Hello, everyone. Welcome. First of all, just want to say we'll be moving relatively quickly. There's a lot of information, so if you have any questions, you're welcome to simply interrupt, or you can, I believe there's a chat on the bottom of the screen here. You can simply post the questions in the chat. I'll do my best to share. Can you guys see the deck here?
Yes.
Okay, very good. Okay, with that, this presentation's been given for Wharton Global Initiatives, Defense Department's, National Defense University Executive Education programs, and for the engineering blockchain course here. So it's a lot of information. Let's jump right into it. Okay, so first of all, why would we care about something like Bitcoin? And the simple answer is that we have these sort of hierarchies in the way our current infrastructure is set up, and it's across all industries. So you think banking, you think healthcare, you think education. There are situations in which the way that the data is exchanged is very much controlled by a third-party intermediary and not by the individuals who that data belongs to. So what we're seeing here is we have these legacy systems where counterparties go through a trusted intermediary to send information or value. And what Bitcoin has introduced is a novel method for that value or information to be shared without that third-party intermediary. And the whole message of today's presentation is, one, how did we get here? What's the technology and the history that got us here, not only in tech, but also in finance and maybe some social events as well. And then how does this technology work? So with that, we'll begin. So with the technology, it was actually here in the United States at the University of Pennsylvania where the first numerical computer was developed. It was called the ENIAC. And it was developed during World War II so that we could calculate the projections of missiles that we fired at the enemy. This sort of age of computer investigation, so to say, or research, it involved all these top researchers from the Navy, from industry, and from academia. And it's largely considered the atomic age. And the reason for that is, as you can see on this image on the right here, what they were doing was they were manipulating atoms, and they were doing it with something called the vacuum tube. And so at a very, very, maybe not in-depth level, a vacuum tube is exactly what you see here. And what it effectively is the earliest computer arithmetic logic unit. So what do we mean by that? Well, you may have heard of something called binary counting, which is base 2 counting. And you've probably seen maybe images or videos and movies you've seen where maybe like the Matrix, it's all these zeros and ones, and it's supposed to show how a computer is making decisions or deciding on certain things. Well, these vacuum tubes were the actual physical manifestations of those zeros and ones that told the computer how to calculate the math effectively. So they're literally tubes with oxygen vacuumed out. And so what that allows it to do is it allows electrons to move around a coil. And the direction of the electrons basically tells you if it's a 0 or a 1. And it allows those electrons to move without it totally burning out. So why is this significant? Well, this launched probably what I would consider the most transformational, or laid the foundation for the most transformational period in technology history, which was the development of the Silicon Transistor. So many of you may be familiar with the very infamous Caltech professor named Richard Feynman. Richard Feynman was the first. There's a lecture called Plenty of Room at the bottom. I would encourage everyone to read it. But he basically came out and said, hey, wait a minute. We're in this age of building big and we're trying to go to the moon, and that's all really great. But look at biology here on Earth. everything is grounded in a foundation of something really small. Us as people, we have cells that make up organs, that make up organ tissue. Amazing. So what do we get from these silicon devices? Well, this is actually what a transistor looks like. And these are specifically what's fabricated on these silicon devices. So you have a silicon wafer, and what they're building is more or less one of these things. And we don't need to get into exactly how it works, but more or less voltage is run through them in a controlled manner. And then what we get is a representation of a 0 or a 1. And we call those bits. As you can see, we have something called Moore's law, which dictates how many transistors we could actually fit onto a chip. It doubles every year, but we're reaching that limit. But maybe this is a better visualization of how consequential this is. If you had a vacuum tube computer that had the same computing power as your iPhone that sits in your pocket right now, it would be the physical size of the entire Pentagon building in Washington, D.C. So that could just maybe give you a little bit of an appreciation of how powerful our cell phones are, and what we have walking around in our pockets. And of course, what did the Silicon Age lay the foundation for? We had companies like Bell Laboratories. I know Bill Cheswick, who used to work at AT&T, is involved. Bell Laboratories became AT&T. He's one of the pioneers. He's involved with the Mentor project. But with the Silicon Age, we had companies like Intel and National and Advanced Micro Devices, a lot of companies that, Taiwan Semiconductor Manufacturing Company, which for reference is the size of 4 Nikes. These are all companies that came out of the Silicon Age. And maybe you're more familiar with the information age companies like Atari, Microsoft, Apple, Amazon, all the companies we're using now. These are all the internet companies. So, what was really interesting about the introduction of the internet is actually the way the information is shared. And the community and the way the community is set up actually informed how Bitcoin development came about, which is in an open way with task forces and groups where anyone can commit an update to the internet. And we'll get more into how that is relevant to Bitcoin in a moment. A few, maybe 2 groups that are worth bringing up from the internet age are RSA. They did a lot of great work with, security algorithms. It became very clear that as we were sharing this data over the internet, the personal data would need to be protected, and it would need to be done by cryptography. And so actually the first internet sort of social movement was a group called the Cypherpunks. And what they were pushing for was for, more or less the US government that had done a huge amount of research into cryptography to actually release those tools for the public benefit. Their mantra was privacy is necessary for an open society in the electronic age. Hal Finney and Julian Assange, 2 household names you may know, were involved with this Code for Good activism. Hal Finney, if you don't know that name, he actually received the first Bitcoin payment back in 2009. Many people have alleged that he is one of the creators. I won't go into that, but he's currently cryogenically actually frozen. He was suffering with ALS. That actually happened this year. So many people in our industry were friends with him, and it's a sad time for his friends and family. Okay, so that's the history of technology that will lay the foundation for how we're talking about Bitcoin. Let's talk a little bit about money. So what makes money? Well, there's a few good sort of hallmarks of money. First of all, it's a store of value. It's worth something. It's a medium of exchange. We can exchange it for something. It's a unit of account. So we use it to, more or less do our books at businesses, then use it as a fundamental unit to measure our economies. And it's fungible. If I have $1, I could break it up in half, and each half would be worth half of a dollar, or I could exchange it for another dollar and it would be worth the same exact thing. An example of non-fungible assets are art, for example. And it's also a standard of deferred payment. So people can issue credit and debit with it. So what are some early currencies? Actually, one of the earliest is what's sort of considered a decentralized currency, is that of Yap in Micronesia, the stone money. More or less what was happening here was, now this is an island in the middle of the Indian Ocean, and households would actually have these huge stones that would sit in front of their house to represent the wealth of the family. And the entire island and everyone on the island would know the whole history of each stone. So each stone had its own value and everyone knew it. And the value was sort of accounted for by the fact that everyone knew it. What's interesting is there was an Irish sailor that, let's say, shipwrecked on this island and introduced different types of tools. And all of the stones that were made after the introduction of these new tools are actually worth less. So it's just an interesting side note. And then we have something interesting coming from China, which is sort of the first rules around counterfeiting. So this has been an issue around currency for the longest time. People are concerned with printing money that were not the authorities. And why were they concerned? Well, the introduction of new money into the economy inflates the currency. Today, with our current banking systems, we have an issue of double spending, where people can actually, because of the way the trusted intermediaries do business, the people that are actually the counterparties do not know if the other person actually has the money they're saying they have to send you. So that person can actually send the same $100 to two people effectively, and that inserts money into the money supply. So Bitcoin was born out of sort of the idea that we need to solve that double spend problem. And of course, central banking of today, without getting too political, naturally there's some concerns about how central banks print money inserted into the supply. Zimbabwe is a great example. Their inflation was in the billions of %, which is just crazy. And in fact, the more independent the central bank is, the less the inflation tends to be. And, again, without getting too political, you can sort of draw your own conclusions as to why. What did the internet do for money? Well, in the 90s, we had the earliest experimentation with virtual currency. The Second Life video game had the Linden Dollar, where people were playing games and gambling. There were some regulatory concerns about that. E-gold, which is a great early project precursor to Bitcoin, tried to associate sort of a virtual currency with actual gold holdings. And of course, the Bitcoin white paper references some of these early projects, one by Nick Szabo, actually, including B-Money and Hashcash. There's more information on that available. And then society, I always like to include this. So, in the early 2000s, we had some situations happen. The first was 9/11, which was obviously a huge tragedy. But what happened in the wake of 9/11 was that there were a lot of freedom of information requests, and a lot of information started coming out about the government, not only the government, but banks, healthcare systems, you name it, education systems. And this contributed to, sort of this eroding of trust in the institutions of, that we all rely on. And then later in the early 2000s, the 2007, 2008, 2009 financial collapse, this was sort of where Bitcoin found its moment. People were concerned with, how much trust we had put into the same authorities that led to the collapse of the economy. And so, all of this is to say, these situations may not have directly led to the development of Bitcoin, but they certainly contributed to its philosophical and political place in our society. And in fact, the first Bitcoin transaction includes a reference to this article by the Times, which references Chancellor on the brink of the second bailout for the bank. So there is a direct reference in the first Bitcoin block to the financial collapse. So how does this all contribute to Bitcoin? Well, I like to go through Bitcoin as two things. First, you know, it's good to say that, you know, Bitcoin was introduced first by a white paper, and the title of the white paper was Bitcoin, a peer-to-peer electronic cash system. So that sort of can set a great framework for how we start thinking about Bitcoin. It was introduced by someone or some group of people named Satoshi Nakamoto. It's still not clear who these people may be. And maybe that was done on purpose by the creators. And then the last thing I'll say on that is that when you're thinking about Bitcoin in a hypothetical sense, Bitcoin is effectively just a number on a spreadsheet. And it's how we change that number and how we consider the worth of that number that makes it something of interest to us. So Bitcoin as money, how we value Bitcoin. What could it be used for in society? Well, is it a store of value? Sure. It depends on how people perceive it. Is it a medium of exchange? People are sending Bitcoin to purchase items at businesses. Is it a unit of account? Sure. Is it fungible? Yes, a Bitcoin's worth a Bitcoin. Is it likely deflationary? So this is kind of in a response to the central banking and how all this inflation's been going on with, you know, the more the government controls that central bank. The way Bitcoin was designed was for it to have a hard cap of 21 million Bitcoin ever. And we'll get into how it's mined and how we're going to get to that number. But that makes it scarce because there will only ever be 21 million Bitcoin. We'll also get into how it's created. So that supposedly the economic theory is that it was intended to be deflationary. Is it a standard of deferred payment? Maybe. Bitcoin's value relative to the dollar is very, very volatile. So I think it's going to take some changing and thinking about how we think about our money for Bitcoin to actually get to be a standard of deferred payment. But there are some good examples where it actually is. So you can ask me about what those are later. And then Bitcoin as technology. So what is Bitcoin? Technically, it's just a number on a spreadsheet, but it's how we change that number that's really of interest. First of all, how we access that number is important. With a bank, we have accounts, they manage our accounts, they store our money, they hold our money for us. With Bitcoin, we have something called asymmetric cryptography. So everyone that has a Bitcoin wallet actually has two addresses. One is a public address that everyone can see, and it's, as it sounds, totally public. I could look up any given public address and find how much Bitcoin it has and its full transaction history. It's how you access the Bitcoin in that public address that's really important, and we do that through asymmetric cryptography with a private key that's uniquely associated to that public key. That private key is also used to sign for transactions. And we'll see how that's important in just a moment. You know, how we change that number is similar to something called a linked list. For you non-engineers, you may not know what that is, but for you engineers, you definitely know what that is. How it's relevant here? Well, changing the number requires your private key signature. And so what happens is when you send a Bitcoin, the whole network is checking your signature to make sure you haven't actually sent that to someone else before. So what does that solve? It solves the double spend problem we talked about earlier, where if you're with a bank, you can actually insert money into the money supply because you can send $100 to two people at the same time. And that would be the same $100. With Bitcoin, that's never possible because the network is checking to make sure you haven't sent that given Bitcoin before. And the way they're checking it is to check your signature for that Bitcoin. So we're going to get into tracing a whole Bitcoin transaction in just a second, and you'll see exactly how this all plays in. There's provenance and trust with Bitcoin. So no transactions, once they're more or less approved by the miners, can ever be reversed. Why is that important? Well, when you don't have that third-party intermediary and you're sending Bitcoin and you're using Bitcoin, you don't want to pay for something or be paid for something, and then the next day that payment be totally worthless. And then how we approve those transactions is through a process called mining. And that's how we've sort of replaced that third-party intermediary more or less, and we'll see exactly how that works in a minute, but we've replaced that third-party intermediary with a whole network of hundreds of computers that don't know each other. So with that, I actually cannot see the chat box. Roger or Michaela, can you guys see any questions that have been asked?
I haven't seen any questions. This is Debbie, but if there are any questions, now's a great time to ask. So you can unmute yourself and ask, or you can put it in the chat box.
Yeah, I'm happy to answer a few quick questions at this point.
I don't have a question, but it looks like the chat box is private, not open to the whole.
Oh, that's odd. Okay, that might explain why I can't see it. So, okay, no problem. I'll keep moving on. But nonetheless, if you do have a question, Debbie, if we can make that chat box open, they could just post it in there. So, and we'll resolve it at the end. So, okay, cool. So, Bitcoin, how does it work? Okay, let's see here. Cool. All right, so first of all, introduced in a white paper by Satoshi Nakamoto, a mysterious developer or group of developers. This is physically the white paper. It's 10 pages. I encourage everyone to read it. Why is it important? Again, we are discussing, oh, here we go. Okay, chat box available. Okay. Why is it important? We're concerned with how data or value is shared. We're moving from this world where, as you can see on the top, the counterparties have to rely on these intermediaries, whether they be banks or transaction processors, to a world where those two intermediaries are actually interfacing with each other, and it's being confirmed by this network of computers all over the world that don't know each other. So let's get into how that works. So first of all, we consider asymmetric cryptography, which we talked a little bit about. Our traditional privacy model is that we all have identities and data, or bank accounts, so to say. We want to send a transaction. We go to the trusted third party, and we ask them to send it to the counterparty for us. And then later, that transaction may become public, or it may be kept out of the view of the public. So this sort of keeping out of the view of the public is the reason why that counterparty and the other side of the transaction will never know if you even had enough money to send them in the first place.
Robert, can I cut in? We have a question.
Sure, sure.
Someone would like to have some clarification. You said he understood that in order to solve the double payment problem, the Bitcoin network that contains hundreds of computers checks your signature. Is this process called mining?
That's a very, very good question. It is one of the things that happens in the mining process. And what we're going to do right now is explain exactly how mining works. So great question. That's one of the things that happens. And we're going to walk through one Bitcoin transaction, and you're going to see exactly how the network works. I'm just laying the foundation now so we have all the tools we need to know what's going on when we do that. So that question will be resolved in just a moment. The new privacy model that Bitcoin presents is that we all have identities, and they're all available to everyone. And then the transactions also are all available to everyone. But it's the identities that allow us to send these transactions, and these identities are, those signatures, so to say, are private, and they're only known by us. So let's get into that exactly. I'm going to skip this because we talked about it a little bit. So proof of work, the mining process. So how is it that we can send a transaction without a trusted intermediary? That is sort of what Bitcoin's claim to fame is this sort of process by which we can actually do that without that intermediary. So one of the things that's implemented is something called proof of work. It is the hallmark of the mining process, as has been asked. More or less what this is when someone submits a transaction, for it to get approved, one of those thousands of computers that can approve the transaction has to do some work. It has to spend some electricity for that transaction to be included in the block. And then once it is, all of the other Bitcoin computers that are running the mining algorithm, which is proof of work, they more or less check the solution and make sure that it's all okay. So I'm actually going to skip ahead here, and we're going to trace through a single Bitcoin transaction and explain exactly how this all works in the context of one transaction. So what happens when someone wants to send a Bitcoin transaction? Well, they have a Bitcoin wallet, and they have a public address. And when they have a counterparty that they want to send Bitcoin to, they actually get the public address of the counterparty. Sorry. Okay. So they get the public address of the counterparty. What happens is the person sending the transaction first indicates how much Bitcoin they want to send. They sign for it with their private key, and it goes into this place called a mempool. And you could think of this mempool as very simply this virtual place where all of these transactions from all over the world, from all these Bitcoin wallets, well, they're sitting there and waiting to get approved by the network of thousands of computers. So first, the user sends a Bitcoin to a counterparty. The private key is used for the signature to sign for the transaction. That Bitcoin is sent to the counterparty's public address, and it goes to, that proposed transaction goes to the mempool. It's not actually settled yet. So it's more or less in wait. It's good to note, now this is a little technical, but there's no actual encryption involved with cryptography, but it's called cryptocurrency because there's some elliptic curve cryptography, so it's called, to guarantee that those private keys and public keys are actually secure. So if you're sort of computer science or engineering savvy and want more information on this, I could send you a great write-up. Just email me, but for now I'm going to move forward. So what happens? So, okay, this is more on the elliptic curve, but nonetheless, what ends up happening is that transaction of Bitcoin, that Bitcoin ended up in the person who's sending the wallet. It ended up there from receiving a transaction. So those signatures, more or less, are how we're actually tracking Bitcoin. We're tracking it actually through a chain of digital signatures. And that's what sort of solves the double spend problem, is that each transaction actually has a history of transactions, and that history of transactions is actually just a history of signatures for that Bitcoin. So what happens now in the mempool? So I mentioned earlier that there's thousands of computers all over the world that are actually sort of maintaining the Bitcoin network. So it's good to note there's actually two classifications for these Bitcoin computer miners, so to say. The first is as a node. Not all nodes are miners, it's good to note. These nodes are volunteers, and what they're actually doing is they're keeping the most recent copy of the entire blockchain on their computer. If the consensus of the nodes agree, then a block created by a miner will actually be added to the blockchain. So what is a block? We're going to talk about that actually right now. But as for, as it pertains to the nodes, the transactions actually get sent to that mempool, that virtual waiting room that we talked about, by a node. So these wallets are sending it through the node to that mempool. Miners. So what is a miner? So some of these nodes around the world are doing something called mining. So not only are they keeping the most recent version of the blockchain, they are also working to add transactions to the blockchain. Now, for now, we could just think of the blockchain as a global spreadsheet of all of the transactions. Once we walk through the mining process, it'll be very clear what exactly we mean by a blockchain. So what does a miner do, and how are they involved in approving a transaction? Well, first of all, the miner works to create a block. This sort of square you see on the middle of the screen here is supposed to be a visual representation of a block. What is it really? Well, in Bitcoin, it's just 1 megabyte worth of memory. And you'll remember from earlier in the lecture, we talked about sort of those silicon transistors or silicon chips. Well, that binary representation more or less is the hardware on which these blocks are stored. So there's actually a physical spend by a computer to create the block. And there's also an electricity spend that needs to go into changing the, changing that binary math to get a representation of a block here to resonate inside the computer. So that's just some context on how the computer engineering works. So what does it mean to create a block? Well, very simply, it's some memory on a computer. And what we're going to put in this block is some information about Bitcoin transactions that we're going to add to the whole global spreadsheet. So the first thing that happens is the miner actually goes to the mempool and starts collecting transaction data from that virtual waiting pool, that virtual waiting room that we call the mempool. The block can actually contain more than one transaction. So these miners are trying to include as many transactions as possible into a single block. And it could also contain data that's not a transaction. There's some great examples of data that's been included on the Bitcoin blockchain, and some great reasons why, which I encourage everyone to Google. But for now, our miners are actually collecting transactions from the mempool and putting it into this memory, this block that we call it. They're actually putting those transactions into the memory that we're calling a block. So what happens next? Well, the miner looks at the blockchain to see what the most recent number of a block is, and then it adds +1 to it and labels this block. So all of the blocks, in the same way that the transactions are sort of traced, the blocks are traced too, and they're chronological and sequential. The next block will always be +1 from the previous block. Now, there's a more complex conversation about hashing and all of this technical jargon, but for now, I think we're going to skip that, although you may see a slide. I forget what order these are in, but you may see a slide in a moment that's exactly explaining that. So each block is numbered. We call that number the hash, and each hash increments by 1 for each additional block. And the block also references, through this hashing process, the previous block on the blockchain that it's referring to. So what does this mean for us? Well, this is the actual physical manifestation of the chain in the name blockchain. So these blocks are getting chained together through this hashing process that simply references the previous block before it. And through that process, the transactions that are in the new block are also referencing the previous transactions for that Bitcoin, or what you should sort of really be thinking about is actually it's referencing the previous signatures that led to that Bitcoin transaction. So each block references the previous block in the blockchain. This chains the blocks together, and this establishes a chronology for the transactions in the blockchain. So what does the miner need to do next? Well, there's something that is involved with each block called a nonce. Now, this word is kind of bizarre. It sounds funny. It's all well and good. This is the actual proof of work that goes on in creating the blockchain. What's happening here is that you have what we call a cryptographic puzzle, and the computer is actually trying to solve that cryptographic puzzle. Now, what it actually is doing, there's no actual mathematical computation, so to say, going on with the solving of the nonce. It's actually guessing a whole bunch of answers until it arrives at the right answer. So that's why you may have heard of like there being a run on, let's say, GPUs or the types of silicon chips that gaming computers were being used for, or you may have heard of something called an ASIC chip. Well, these sort of computer processors are designed to guess numbers much more quickly. And they're able to process those numbers more quickly. So that's why miners want the fastest sort of processing chip they can find, because they need to solve that nonce as fast as possible to get as many blocks sort of proposed to the whole blockchain as possible. And if you think back to what we talked about earlier, those chips that we're talking about here, these ASIC chips, they're just silicon chips with billions of transistors fabricated into them. So that's how all of that sort of history plays in here with the computing. So what happens? Well, you need to solve this puzzle. The miner needs to solve the puzzle for it to be added, for the whole block to be added to the blockchain. And so what happens after they solve the puzzle? Well, they've effectively done their proof of work. They've spent their electricity to solve the puzzle. Here's some more on proof of work. We'll skip this slide. Here's your hashing. But effectively what happens now is this goes back to these nodes. That block that the proof of work has happened for goes back and gets proposed to all the nodes, and the nodes basically check the answer. They check to see if the answer is right of the cryptographic puzzle, and then if it is right, what do they do next? They check that all of the signatures are valid. So they check to make sure that every transaction that has been included in that block has a signature that doesn't represent the transaction signature for Bitcoin that's been spent in a previous block. So that sort of guarantees, that's more or less the process that guarantees that we can have a peer-to-peer, a peer-to-peer counterparty interaction with all of these thousands of computers that don't know each other. Now, how is that relevant? Well, because the computers don't know each other, there is a sort of incentive not to collude. And the reason for that is that when this block gets approved, well, the miners spent electricity. So what should happen for the miners is that they should get paid some newly minted Bitcoin. And that's how sort of Bitcoin gets inserted into the money supply. And that's why we are referencing this deflationary idea. I'm going to show you a chart for that in just a moment. I just want to clarify and explain once again. So what happens is a Bitcoin miner creates a block. It's a bit of memory on their computer. They then go to that virtual waiting room, get a bunch of transactions. They include it in the block. They then effectively label the block and reference the previous block that is publicly known to be the previous block, which effectively changed this block to that previous block. Then they solve the computer cryptographic problem, and in doing so, they're spending electricity. And the reason why we're requiring that electricity spend is, more or less to make sure that each miner is acting in good faith, and to, sort of, what's the word I'm looking for? Disincentivize any collusion. So that is how the Bitcoin mining process works. Let me just skip ahead here. We're going to skip that. Yes, so effectively, this is what happens. A new transaction issued by someone with a Bitcoin wallet gets broadcast to all the computers, all of the nodes on the network. A miner will collect the new transaction into a block. They will then work to solve that difficult proof of work for that block. When it finds that proof of work, the cryptographic puzzle, it broadcasts that block and the solution to all of the other nodes. And then the nodes accept their acceptance of the block, not by voting. This is a big misconception. People think that it's a consensus by vote of each block. It's not true. It's actually consensus. The other miners are voting by including that block on their publicly available version of the blockchain, their most recent copy, and then by working on the next block that references this block that we just proposed. So that's how the consensus works. You know, by virtue of the miner presenting its block to all the other miners, each miner keeps the most updated version of the blockchain on their computers at all times. And this sort of enables this decentralization buzzword that we keep hearing about. Because the miners do not know each other, they're incentivized to actually compete to add those blocks with integrity. So you would need to have 51% of the computing power on the Bitcoin network to take control and sort of reverse these blocks. And that's why we say these blocks are immutable. They can never be changed, because no one of these miners is actually able to go back and change a Bitcoin transaction. How would they change a Bitcoin transaction? They would need to hack into every single node on that network and make that change, which hacking into one computer system happens all the time in our current systems, in our legacy systems. Think about the Equifax hack. All of our personal data was just stored on one database. In this scenario, the data, much of it is public but anonymous. But to change the integrity of that data, you need to hack into thousands of different databases. And that's something that is so difficult. You would need to have to spend, this estimate's totally wrong, but to give you sort of an idea, a hypothetical idea, you would need to spend the amount of electricity Nigeria spends in a month as a whole country. You need to be able to spend that in a day to get that, to make those changes and hack into the blockchain. So that's why we consider this blockchain thing to be more secure, so to say, that in terms of its data integrity. So we try to solve the double spend problem. That is the major takeaway of Bitcoin. And we ended up with something called a Byzantine fault-tolerant system. So what does that mean? Well, the Byzantine war generals problem, more or less can be thought of, you have all of these sort of, platoons of soldiers all over the globe fighting a war on your behalf, but it takes you a while for you to communicate with them. And then on the way to communicate with them, those communications could get intercepted or they won't end up there. You could sort of understand where that problem comes in its, the history as a war issue, but in a modern issue, we have that same problem with, sharing data. And so what Bitcoin presents is a way to actually make sure that all of the thousands of computers, or at least the consensus of those thousands of computers, all agree as to what the most recent version of that data is. So there's a global acceptance of what the data is in a way that we didn't have before. In legacy systems, you would need to actually physically send a file over to another computer. So that's what makes this Bitcoin thing really interesting. So how do we get to a Byzantine fault-tolerant system? Well, we have elliptic curve cryptography, which ensures a secure system of digital signatures. We have our nonce, which forces the computer to do computation to approve a transaction and earn a reward. And it ensures, we want to think about why it's, why the miners not incentivized to cheat or try to reverse transactions. It's always going to be cheaper for the computer to spend electricity to add one block to the blockchain than it is for that computer to spend the electricity to reverse 5 blocks. So you can imagine if you want to make a change to that blockchain, that computer actually needs to spend the electricity for each block going back to whatever it wants to change. So that's why it's immutable. And then we have this thing called SHA-256, which helps ensure, and this is a cryptographic tool, but this helps ensure the most recent version of the blockchain is always uniquely represented. This is the hashing thing that I mentioned earlier, but it's a little too, I think, technical for us to get into. This is used, though, to establish our consensus and our truth about what the global version of Bitcoin is at any given time. So what have we done? We've solved the double spend problem. Users have ownership for the first time over their assets. It's not a bank that's holding your money for you and giving you a representation in an account. You actually own your Bitcoin in your wallet, and the only way to access it is through your private key or your signature. And the full history of the ledger is available to anyone who wants to see it. So because those public keys are anonymous, something that's really interesting is that data is actually publicly available for each wallet and their transaction history. That's also how we help check those previous transactions and signatures. Now, I mentioned a little bit about Bitcoin being sort of deflationary in nature, and I mentioned about the miners getting paid newly minted Bitcoin. So this graph, which is actually taken from Wikipedia, I think is one of the best representations of this. You know, what we have is, as I explained earlier, that Bitcoin miner gets paid a miner's reward. Newly minted Bitcoin that had not been in the circulating supply before, they get paid that when a block is successfully sort of included in the Bitcoin blockchain. Now, how is that miner's reward determined? Well, we have a half-life on that Bitcoin miner's reward. So it actually started, I believe it was 50 Bitcoin was the miner's reward. And every 210,000 blocks, this miner's reward actually cuts in half. So new Bitcoin entering the supply cuts in half every 210,000 blocks. Those miners then make half as much Bitcoin as they do previously for each block that they add. So what does this do to the Bitcoin supply? Well, that half-life gives it a maximum supply of 21 million Bitcoin, and really it's like 20.999999 million Bitcoin, but there's a maximum supply. So you can think about sort of the philosophy, we spoke about some of the societal impacts and some of the things that contributed in terms of monetary theory and central banking, the type of thinking that went into the design of Bitcoin and how it informs or how it informed its development. So where are we at right now? Well, the Bitcoin miner reward currently stands at 12 Bitcoin. And actually in May, we're coming up on another event where the Bitcoin miner's reward is going to be cut in half to 6.25 Bitcoin. Cool. So you can see here another good representation of this, this block reward cutting in half. This is let me see this here. This is a logarithmic chart, but you can see that it's cutting in half every 210,000 blocks. Cool. So what other things can we do with stuff like this, with these technologies? Well, Zcash and the zero knowledge proof, that's another good use case of sort of cryptography and its impact. The founder of Zcash, Zuko Wilcox, was actually he was involved with the Cypherpunks, I believe, early on, or at least he, actually, no, yes, he was, almost certainly. I had a discussion with him in Croatia this last summer. So, if you want to take these privacy technologies a step further, there are things called zero knowledge proofs where there's sort of a verification process that the transaction data is legitimate, but you're not sharing even any identifying information with the counterparty. So if you want to do more research on that, that's another good example. Transaction fees in Bitcoin, people think there's a fee every time. I think that's a misconception because people use exchanges to access Bitcoin, and what they're actually paying is an exchange fee. There are actually no transaction fees for Bitcoin for the sender, the owner of the wallet, but they may opt, it's optional, they may opt to include a tip to the miner for them to include their transaction in an earlier block. So you can imagine, you know, how many transactions are waiting in the mempool. Some people want to settle their transaction more quickly. That's when you see sort of, you know, when there's a large volume of Bitcoin transactions waiting, that's when you see sort of a spike in these sort of optional tips. Okay, so that's how Bitcoin works. The second hour of this lecture, and Debbie, if you guys are open to it, if this had good feedback from the people that came, I'm happy to get into some of the sort of more business use cases and what the same principles mean in terms of another great technology called Ethereum, which is kind of like Bitcoin, except with Ethereum, we have these things called smart contracts where the counterparties can actually enter into agreements that get automatically executed when some data input is sent to that contract. So no longer is a third-party intermediary needed to approve a contract. So that's a really interesting thing that has a lot of use cases. There's a lot of different comparison, a lot of good use cases I'm happy to go into. But with that, we have covered exactly how Bitcoin works. And I think for the last 5 minutes or so, we can open it to questions, and I'm happy to answer questions.
I have one that's in the chat. Can you say a bit about the Byzantine Generals problem?
Yes. So the Byzantine Generals problem is a problem with data sharing. Now, I must preface this that the answer I'm going to give you is sort of not a very in-depth engineering answer, but this is basically what the problem is. The problem is this. We have databases all over the world that store data. And when we want to send data to another database from one computer to another computer, there are sort of situations in which that data can get corrupted or intercepted. If you want to think about it in a business sense, so that's sort of an engineering sense. In a business sense, you're managing 4 different teams. How do you make sure every team is most up to date on the current situation and strategy at every given time? So what Bitcoin, how Bitcoin solves this problem and becomes fault tolerant is simply in its consensus mechanism, where it requires a consensus of all of those thousands of computers all over the world to agree as to what the most recent version of that blockchain is, of the spreadsheet is. And that makes sure that no matter what, no matter how many thousands of computers there are, there's only ever one blockchain that's considered the blockchain that these miners are adding blocks to. And I'm looking for a slide that I think is really good to help picture this. One moment. Here we go. It's called the longest, most honest chain principle. So you could imagine there are, you know, thousands of computers trying to add blocks at any given time. Well, what happens when 2 computers try to add the same block that references the same previous block and it's of the same block number? Well, that's okay. And it happens all the time. But what ends up happening is the Byzantine sort of fault, the Byzantine fault tolerance comes in with respect to, we are hard-coded to knowing that the highest block number is the block that all of the miners should add to. So there will always be a situation where there is a longer block than the previous ones. There's a longer blockchain than the previous ones, and all that means is that that sort of block number is higher than the other ones. And that is what's considered to be the globally accepted blockchain. Why is it that we globally accept that to be the blockchain? Well, all of the miners, the algorithm, it's hard-coded for them to simply look for that highest number and add to it. So that's how we guarantee the longest, most honest chain principle. And that's how we resolve the Byzantine Generals problem and making sure globally that there's just one version of the blockchain or the spreadsheet.
We have a follow-up question.
Sure.
I've seen different percentages, but for the Byzantine Generals problem, I think you need more than 51% of generals to be loyal. What is the 51% attack?
That's a very, very good question. So the 51% attack is one of the vulnerabilities of Bitcoin. And effectively, what it means is this. The consensus, okay, let me just preface this. The reason why you've seen different percentages is that each one of these blockchain networks, whether it be Bitcoin or Ethereum or, Bitcoin Cash, any blockchain that you see, they all have their own sort of rules. And so some of these blockchains will have different thresholds for that consensus, that percentage of agreement. Another reason is that now I mentioned earlier the Internet Task Force and how anyone can contribute a software update to the internet. Well, the same principle is here with Bitcoin too. Anyone can actually contribute an update to the Bitcoin source code, but the community can actually agree to a different sort of percentages of miners that would need to accept that update to the Bitcoin source code to make that update go into effect. So there are a lot of good examples of what those updates can be. But that's why maybe there's some confusion as to what that percentage is. But what is the 51% attack? Well, you remember earlier, I said that a consensus of miners need to quote unquote approve the blockchain or approve the block that gets added to the blockchain. Well, there's no actual voting and approval. There's just the miners actually working to add the next block to the blockchain. And if at least the consensus, 51%, is adding that block to the blockchain, then it's considered the longest, most honest chain as we see here. Now, what is the 51% attack? The 51% attack is if one nefarious actor takes control of more than 51% of that computing power and starts adding blocks to the blockchain, they would have total control and would be able to reverse some of these blocks. And why is that? Well, they have effectively they have the consensus of the miners in their power, and they have at least 51% of the mining power to be able to dictate what blocks get added and how the longest, most honest chain is perceived, so to say. So I hope that answers your question about what that 51% attack is. It's a fascinating thing. It is one of the vulnerabilities of Bitcoin, excuse me. And it's something that, it's something that maybe makes sort of having thousands of computers not knowing each other very, very important to making Bitcoin successful. So that's where that sort of decentralization concept comes in, making sure that people, don't know each other so that they're not incentivized to collude in this way, take over the mining process, and, effectively change transaction data at whim. Does that answer your question? I hope it does. So.
I have another question for you.
Sure. Can
you tell us about your company, AlphaGora?
I can. Actually, the whole AlphaGora team is on the call. So maybe I will defer to one of my colleagues, since a lot of you have heard my voice for a little, for an hour straight. Michaela, Roger, Alex, do one of you want to give the pitch here? Maybe Roger, you want to do it? Let's see.
Sorry,
I think
guys.
it's all you. Oh,
yeah, I was on mute as well. Yeah, I'm here. So yeah, I guess quickly, because we're running out of time, AlphaGora is focused on the idea that as more people adopt cryptocurrencies, there's going to be a need to exchange these currencies with one another. And ideally, that happens through, an exchange. And as a result, you'll be trading these currencies more frequently, just like we have in a stock market. You're trading cryptocurrencies on a crypto exchange. And so AlphaGora is built to provide automated trading tools to help you execute these trades in an automated fashion, and we rely on quantitative strategies so that your trades can be based on mathematical principles and patterns of the market. So in a nutshell, we help you manage any crypto that you have that you might want to actively trade in the markets through automated trading tools.
Very good. Thank you, Roger. Any other questions? Okay, Debbie, if there are no further questions, you're welcome to share my email with anyone from this lecture that wants to reach out with further questions or has any other questions related to Bitcoin. I'm happy to explore doing a second session and getting into some of the business use cases in Ethereum. So just let me know if that would be of interest.
Yes, I'd love that, first of all. So let's just say yes now. But also, can you just share right now your email and any other areas that people can reach you on social media or other places, and your website for your company, so that we can share that online?
Sure. So my personal email, Debbie, I would just ask the attendees to reach out to you personally, because I know this is going to be made a public video. But our company website is alphagora.io, so www.alphagora.io. So if you want to learn more about what we're doing, you're welcome to visit there. We started the company last year. We have a great team. I think that's what has made it so successful thus far. And we're really excited about what we're building. So if that's something of interest to you, you're welcome to come. And I will say this, on the data being public and anonymous. So there's a lot of outstanding business use cases just for the data alone. Let me just go ahead here. 1 second. Okay. So there are companies like Elementus that are tracing those. You remember we talked about Bitcoin as sort of a sequence of digital signatures. Well, that gives you sort of information about how money is sent from person to person. And even though it's anonymous, there are different situations where you're able to identify companies involved with the transaction. And you could actually trace that transaction data and the wallet data to determine different patterns of fraudulent activity even. So if you go to a website, they're called actually, same way Internet Explorers, block explorers. Block explorers allow you to see all of the data going back to the first Bitcoin transaction on the Bitcoin blockchain and for any blockchain. So that might be an interesting follow-up for everyone as well.
Absolutely. This was great. I really learned a lot, and I honestly have to say that I don't have any background in this, and I found it fascinating from beginning to end. So